them up today. Yeah, so I kind of already said that. Empirical formula, you have a note sheet that should have shown up, which you can type on if you want. I would strongly suggest just doing it on a piece of paper as you follow along, but you can use my note outline if you want to. And I need to get into the right class, so I need to get rid of that one. All right, so here we go. Empirical, oh, not Kepler's laws, wrong class. Let's go. Empirical formula. What the heck is empirical formula? Hello. There it is. Goodness gracious. Must be the end of the day. Okay, so we've done percents. You know that percent should add up to 100. You know that compounds can be made of lots of elements. We'll keep it simple with 2 or 3 for most of this early work, but you might see 4 or 5, 6 elements in the same compound. It's possible. Empirical formula, what does it show? Well, empirical is a term that means by experiment or, yeah, by observation. You have found it yourself, okay? And so for me, it's easiest to remember E for empirical, E for experiment. So what data have you collected on your own? Empirical formulas show you the smallest whole number ratio of the atoms in a compound. Now, some compounds, it's really simple, like water. When you look at a formula, the formula for water, there's a subscript for the hydrogen, and there's no subscript for the oxygen, so it's understood to be 1. That means for every 2 hydrogen atoms, you have 1 oxygen atom. It's a 2-to-1 ratio, which is also a proportion, which is also, you can think of as a fraction, right? All of these words kind of are interchangeable. If I asked you to put the proportions of hydrogen to oxygen or the fraction representing hydrogen to oxygen, you could do it with a little colon. You could do it 2-to-1 as a fraction. Sometimes that's not the actual formula of the molecule. For water, this is the empirical formula, and it's the molecular formula. Now, what the heck am I talking about? So ionic compounds like salt, my little salt model, has sodium ions, has chloride ions. There's 1 sodium for every chlorine. But if you analyze a salt crystal, every sodium ion is surrounded by 6 chlorides, and every chloride is surrounded by 6 sodium. So you might be tempted to do something like that. Like, remember when we were doing the crisscrossing with magnesium and oxygen, +2, -2. People want to do, just bring the numbers down. But what would your math teacher tell you if you did a proportion 2-to-2 or 6-to-6? Or simplify it, reduce it, simplify it, make it 1. Okay, so the simplest way to represent how many sodiums and chlorines are with each other, it's 1 for every 1. Same with magnesium and oxygen. So ionic compounds do it automatically. Unfortunately, there's some crazy molecular compounds that are, especially in organic chemistry. Right, and these are 3 examples. So there are 3 different compounds. There's more than 3, but these are 3 that we're going to look at that have only carbon, hydrogen, and oxygen. And so there's something called ethanoic acid, C2H4O2, 2 carbons, 4 hydrogens, 2 oxygens. There's also something called methanal, CH2O, 1 carbon, 2 hydrogens, 1 oxygen. And there's one that you should be familiar with from last year, your friend glucose. All you smart people burning the glucose in those brain cells. And you look at those and you go, wow, those are really different. Well, they're not. They only have the 3 elements. They all have the same 3 elements, law of multiple proportions. If you did 2 to 4, your math teacher would say 1 to 2, right? Reduce it. And if you said 4 to 2, they'd say fix that, 2 to 1, right? Same thing here, 6 to 12. It's the same as 1 to 2, 12 to 6. Okay, and they all, this one has it, but automatically, or as the real molecule, they all have the same proportions of carbon to hydrogen to oxygen, equal numbers of carbons as oxygens, twice as many hydrogens as either carbon or oxygen, okay? But they're in multiples. So this is the real molecule in blue. Empirical formula is the 1 to 2 to 1. This is twice as big. This is 6 times as big. They're just multiples for the real molecules. So how do we do calculations with these? Why do we do calculations with these? Well, back in the old days, they're just breaking stuff up, figuring out what stuff is made of, and seeing how much of each thing they have. And then from that, deducing how many atoms of each element are in the compound. So we're going to start with an example problem, because I think it's just as easy to do this with a problem as talk through it. And Bethany, would you read the problem, please?
A compound is analyzed and found to contain 25.9% nitrogen and 74.1% oxygen. What is the empirical formula of the compound?
Perfect. So we've done percent composition. So something has just nitrogen and just oxygen, about 3 times as much oxygen, if you will, as nitrogen. And you know that percents add up to 100. Bloop. Anybody see what the text is?
It's Haley. She said she got kicked out. She started.
Okay, thank you. So percents are easy, I hope, for you. But we can't do anything with percents. There's no relationship to percents in moles, for example. So we want to get a count of how many nitrogens and a count of how many oxygens are in a unit of this stuff. So the very first step we're going to do is a super simple one. So just write down step 1, change percent to grams, if that's what you're given. Sometimes you'll be given a mass automatically, or you'll do the analysis yourself and have a mass value. But in problems, they do percent a lot. So it's as simple as just swapping out the percent symbol for grams. Really easy. So if we had a magically perfect sample of exactly 100 grams of this compound, 25.9 grams of it would be nitrogen, 74.1 grams would be oxygen. Easy enough, right? Yeah. Step number 2 is, if we're wanting to count atoms, we have to change grams into moles. Good job. So we're going to go ahead and, oops, I don't want to show you the answer yet. We're going to change the grams into moles. So 1 mole of nitrogen has a certain number of grams, and 1 mole of oxygen has a certain number of grams. And of course, you get those from the periodic table. Imagine this number is over 1. Grams, cancel grams. We all know, I hope we're getting to know that oxygen 16. And same thing for nitrogen. Grams on top, cancel grams on the bottom. We're left with moles. And the value for nitrogen is what? Gwen?
14.01.
Beautiful. So remember, we could count individual atoms, but who wants to deal with scientific notation? Okay, it's really a pain. So we're going to just get ourselves into moles. and then compare. It's like comparing dozens of things, okay, or comparing moles of them. So go ahead and push that through your calculator. What'd you get for? What did you get for nitrogen, Lauren?
4.63.
Beautiful. 4.63 moles. Okay. We have more than one. Oh, that's oxygen, right?
Yeah, that's what I got for oxygen.
Yep. We have more than 1 mole of both of these. We have 4.63 moles of oxygen, and we have 1.85 moles of nitrogen. Everybody concur? We could multiply this by 6.02 times 10 to the 23rd and then deal with it, but that just is making things harder than it has to be, okay? So all we're trying to do is use the count. So this many atoms of nitrogen go with this many atoms of oxygen. You will not see subscripts like that for a couple of reasons. One, they're really hard to work with, and two, you can't have part of a nitrogen atom or part of an oxygen atom. Okay, we need whole atoms. So how are we going to get these numbers to be whole numbers is going to be the next step. We're going to divide by the smallest number, right? The fastest way to get a whole number out of this one is divide it by itself. Okay. If we divide the other one, we have to, if we divide one, we have to divide the other one. Okay. And that's not numbers that are readily apparent, at least not to my brain, but all of you, I hope, will see that it's 2.5. Everybody good with that? So for every 1 nitrogen, there's 2.5 oxygens. Again, I can't have a half an oxygen. I have to have a whole number. So 1 to 2.5, if I want to make 2.5 into a whole number, 2.5 into a whole number, what's the easiest way? Anybody? Multiply it by 2. Okay? And if we multiply it by 2, the 1 becomes a 2, and the 2.5 becomes a 5. These then are the whole numbers of atoms in proportion to each other. And you can prove it to yourself. It doesn't quite come out because of rounding, but if you took 1.85 divided by 4.66 and then do 2 divided by 5, they'll come out close to 0.4. I think this is 0.398 or something. So they come out to the same proportions. It's like doing a recipe. You know, this is 1 serving and I want 2 servings or whatever. Okay, you have to multiply both parts. Excuse me. All right. Okay, so what did that get us? That got us what's called an empirical formula. Sometimes that's the formula of the real molecule. Sometimes that's the right number of atoms of each element. Sometimes you have to multiply it. So these are all the steps again. I'm not going to go through them. Hopefully you got them down. Okay. All right, let's try one on our own. 1,6-diaminohexane. What the heck is that? It doesn't matter. It's something. Okay. They've got the percent composition. See if you can come up with the empirical formula.
What was the last step? Use these whole numbers at subscripts.
Uh-huh.
That's it?
Yep. So it is carbon, 62.1%, hydrogen, 13.8%, nitrogen, 24.1%. Feel free to talk to your neighbors, see if they get the same thing. My goodness. Remember, the first step's the easy step. Just make believe everything's in grams.
I was like, what do you? I didn't know what you're dividing by, but that's just the mass, right?
One more time.
No, I got it.
Okay.
I did. It just makes sense.
So obviously you need your periodic table to find the molar mass for the element. So I did, most of the calculations are to the tenths place, but then went to the thousandths place. I don't know what I was doing when I put this together, but anywho, I haven't had a chance to fix it today. So Jack Birtwistle, what'd you get for moles of carbon? Oh, sorry. Monty, did you get moles of carbon? 5.17 moles. Everybody agree?
Yep.
Okay. How about 4 moles of hydrogen? This is going to depend on whether you do the 1.01 or the 1. I mean, it is 1. It's close enough, but I think it's 13.66 if you use 01. And I forget what the other one is. Aiden, did you get nitrogen yet? 1.72, that's right. Okay, so again, you can't use these for subscripts. That gets them in proportion to each other. Okay, rough proportions, but it's not a whole number. You have to have whole atoms. So how can we make it whole? We can do divide by the smallest one. Colin, what do you get for carbon? Okay. Yeah, so we'll just call it 3. Okay, everybody good? All right, and then for hydrogen, what'd you get, Jack? Conte? 7.94. So this is a classic of like, what do I do with that? That's not an easy multiple. You can't just, double it and get a whole number. It's also, the classic marketing scheme, right? You go into Walmart, it's $1.96. It's not really $2. Okay, you know, it's $12.99. It's not really $13. Okay, so it's if it's off in the hundredths place, we can go ahead and round it up. So this is 3, this is 8, and this is 1. Now, if it was 1.2, something like that, then you'd have to go by 5. Okay, that would get you to a whole number and a few pennies, right? But when it's in just in the hundredths place like this, we just kind of ignore it and round. Okay. So again, what does that mean? That means there's 3 carbon atoms for every 8 hydrogen atoms with every 1 nitrogen. 3 to 8 to 1. That's the empirical formula, and it should weigh a certain amount. It should weigh 3 times 12, 8 times 1, and 1 times 14. It should weigh somewhere around 58 grams per mole. If I told you it's 116 grams per mole, the real compound, everybody understand where I got these numbers?
Yes.
Okay, so if I told you it's 116 grams per mole, 58 is half of that, right? This is twice as much. That means the real molecule would be twice as big. So this is empirical. This is just the raw data, simplest reduced fraction stuff. But the real molecule is C6H16N2. And you can't figure that out unless someone gives you the molecular mass, okay? And that's where we're going to go tomorrow. I don't want to take too much more time on that. I can also get it from the name. So if you read the name with me really quick, just look up there, 1,6-di-amino hexane. Hex is 6. That has to do with the carbons, 6 carbons. And amino, whenever you see amino, like amino acid, that means it has nitrogen in it, right? So diamino hexane, that's from the name, I can figure that one out. You can't, yeah, maybe you can. Maybe you can now that I showed you. But we're going to learn how to take empirical formulas to calculate molecular formulas. I guess tomorrow. Let's see. Again, molecular formula is what the real molecule weighs. Like we looked at those first ones, the ethanol and the methanol and all that stuff. There's in the same proportions of carbon, hydrogen, oxygen, but there's multiples, okay? The molecular formula will always be a multiple. Usually it's 2 or 3, maybe like glucose is 6 times as big. That's not that common, okay? But there are always some whole number multiple of the empirical, because we have to have whole atoms. 2 times 3 is 6, 2 times 8 is 16, 2 times 1 is 2. Okay? And that's how that piece works. Just really quick, I'll show you this because it's kind of cool. Acetylene is properly called ethine. Eth means 2 carbons. Ine means there's a triple bond. But some of you probably have at least seen somebody welding. Anybody do welding? Acetylene torch welding? No? Oh, it's really cool. Or it's really hot, but yeah, anyhow. So there's carbon with triple bonds and then hydrogens, C2H2. Right? 2 to 2, and your math teacher just says, no, dummy, it's 1 to 1. It's 1. Okay. Polystyrene or styrofoam is a molecule that has 8 carbons with 8 hydrogens. Crazy structure, has a hex ring, and then it has a double bonded carbon thing here and some extra hydrogens, and not all the hydrogens are shown. But again, it's 8 to 8. That's the same as 1 to 1. Okay. And so for every carbon, there's a hydrogen. And they have the same empirical formula, but they have different molecular formulas. One's a gas and one's a liquid, and then they puff it up with carbon dioxide. I used to use chlorofluorocarbons to make styrofoam. All right. Same molecular formula, excuse me, different molecular formula, same empirical formula. All right, I'm going to stop right there if that's okay. Like, whew, yes, please. All right, and let's look at our lab. Why does that keep showing up? I think everybody got the data on Friday, but just in case. Those of you at home, I had you use these numbers for your team sample. And then you're doing percent errors. I think that's where we left off Friday. And then we pooled our data. So what you're going to do is use the class pooled percentages to do the last problem. I'm not going to go through and do them all. Okay, so this the strawberry came out 22.76. Looks like the orange is going to be below that. Orange and brown or grape are basically the same. Green, apple, and yellow are going to be, looks like yellow is really close to 20%, huh? So when we pool our data and have lots of samples, we get closer to the accepted result. That's kind of something you want to talk about in your conclusion. You do not need to do the class percent error. I was just showing that to you on Friday. Okay. So right here in part 7, I want you to use the class pooled percentages for your calculations. If we use the manufacturer's values of 20%, all the answers would be the same. Be kind of silly. So the 2,268 gram bag has, based on our analysis, 22.76% strawberry. But we don't use percent in the calculation. The book tells you to divide it by 100. So you can do that. Multiply the 2,268 times 22.76 and then divide by 100. Or smart people make the percent into a decimal, right? 2,268. And just multiply, because otherwise you have to multiply and divide. If you mentally move that decimal place, you can just multiply. They should come out to be the same. So let's just do it. 516.20 grams out of that bag should be red strawberry. Okay. And so you just have the other 4 to do, and then the paragraph to answer about what was the purpose, why do you think your percent didn't match the factory numbers, how does your team value compare to the class, were you higher or lower or the same, and then why do you think this relates to what we're doing in chemistry. Okay. So 7-8 sentences tops is all you need in your conclusion. I don't need a huge story, okay, but just a little bit to sum it up and finish your calculations. So we also have the green apple already calculated, so I'll just go ahead and highlight that. Questions I can answer. Anybody that needs help, what can I help you with? Let me know.